Okay, we've seen the basics of a BJT transistor operation and what it takes to bias a transistor into operation. So let's look at something called a Class A amplifier using the bipolar junction transistor. DC bias allows a transistor to operate as an amplifier. In a Class A amplifier, the transistor conducts for the full cycle of the input signal or across 360 degrees. Thus, a transistor can be used to produce a larger signal using a smaller signal as a pattern. So, we're going to look at this basically something modeled as a sinusoidal input that continues to um, to provide a signal as an input. In this section, we'll discuss how a transistor acts as an amplifier and examine a basic amplifier. So let's examine the factors important in the operation of a transistor Class A amplifier. Generally, Class A amplifiers are used in low power applications where power levels are generally less than 1 watt. So let's look at the collector characteristic curves. So we've seen the characteristic curves associated with the diode. Let's see what they look like for the transistor. Using a circuit like the one shown, you can generate a set of collector characteristic curves that show how the collector current I sub C varies with the collector to emitter voltage VCE for specified values of base current IB. Notice in the circuit diagram that both VBB and VCC are variable sources of voltage. Okay, so if we take a look at that, we can see, as indicated, we've got VCC, a variable DC source, VBB, a variable DC source. So we've got this set up with a resistor on the base, and this typically will be our bias point for the transistor. So we can see here from this what we've got in terms of current flow, IB, and I sub C. So if we look at the collector characteristic curves, we can see in this example B, we've got one of a family of curves that are produced. Once the diode is triggered into conduction via the 7/10 of a volt bias, and then across what's called the active region. This region we'll find out is the case where we want to operate so that we're not operating into saturation. The more we move along this curve out to this point C, we start getting into saturation and distortion. So we've got the saturation region, the active region, and the breakdown region. So depending on what we input on the base of the transistor, you can see we've got I sub B 0, 1, 2, 3, all the way out to 6. And this is showing what they call a family of I sub C curves versus VCE curves for several values of the I sub B, the beta or base current. So if we assume that VBB is set to produce a certain value of collector um, base to collector current and voltage I sub B and VCC set to 0. For this condition, both the base emitter junction and the base collector junction are forward biased because the base is approximately at 7/10 of a volt, while the emitter and collector are at 0. Most of the base current is through the base emitter junction because of the low impedance path to ground. When both junctions are forward biased, the transistor is in saturation region in this operation. So if we look at that, in the diagram here, we can see this small area here is the saturation region. We want to be here in the active region, as we'll see later. As VCC then is increased, VCE increases gradually as the collector current increases. This is indicated by the portion of the characteristic curve between points A and B. I sub C increases as VCC is increased because VCE remains less than 7/10 of a volt due to the forward bias base collector junction. Ideally, when VCE exceeds 7/10 of a volt, the base collector junction becomes reverse bias and the transistor goes into the active or linear region of its operation. Once the base collector junction is reverse bias, I sub C levels off and remains essentially constant for a given value of I sub B as VCE continues to increase. Actually, I sub C increases very slightly as VCE increases due to a widening of the base collector depletion region. This results in fewer holes for recombination in the base region, which effectively causes a slight increase of beta DC. This is shown by the portion of the characteristic curve between points B and C in the figure. For this portion of the characteristic curve, the value of I sub C is determined only by the relationship expressed as I sub C equal to beta DC IB. So we can see that in the diagrams here. So between B and C, which is everywhere in the active region. When VCE reaches a sufficiently high voltage, the reverse biased base collector junction goes into breakdown, and the collector current increases rapidly as indicated by the part of the curve to the right of point C. A transistor should never be operated in this breakdown region for the same reasons as not operating a diode in the breakdown region, in the reverse breakdown region. A family of collector characteristic curves is produced when I sub C versus VCE is plotted for several values of base current I sub B. When I sub B equals 0, the transistor is in cutoff. Although there is a very small collector leakage current as indicated, the amount of collector leakage current for I sub B is 0 is exaggerated on the graph. So if we look at a quick example here to illustrate the family of collector characteristic curves, draw the family of collector characteristic curves for the circuit, and assuming that I sub B is equal to 5 microamps to 25 microamps in a 5 microamp increment. Assume that beta DC is equal to 100. Okay, so they want us to look at the range, the family of curves between 5 and 25 microamps. So using the relationship I sub C is equal to beta DC times IB, you can calculate the ideal values of I sub C and tabulate in a table. So you can see over here we've calculated beta DC 100 times each of these values. So 100 times 5 microamps gives us half a milliamp. 100 times 10 microamps gives us 1 milliamp. 100 times 15 microamps gives us 1.5 milliamps, and so on. So those are our increments. So when we plot them, we end up with a family of curves that looks like this. So you can see for each one of these 5, 10, 15, 20, 25 microamps, we end up then in the milliamp range for our values for the curves. Generally, the characteristic curves have a slight upward slope to them, and you can see that here, and they're not flat. They're flat, but they're angled up. This indicates that for a given value of I sub B, I sub C increases slightly as VCE increases, which implies then that beta DC is not exactly constant. Okay, so the family of curves. So when we'll come back, we'll take a look at saturation and cutoff.